Hello, and welcome to Kennedy Space Center here in beautiful Florida, where tomorrow night we're going to be launching the OSIRIS-REx mission aboard a ULA Atlas V to go visit an asteroid. Today we're going to go and dive deep into the mission and learn a little bit about the science behind it, what we're trying to accomplish, why are we visiting an asteroid, and answer a lot of different questions that are around this mission out here. For those of you who are joining us online, you're welcome to ask questions during any of our Q&A sessions using the hashtag AskNASA. And this is part of an overall event down here at the Kennedy Space Center for 2 days with our social media followers called a NASA Social. We invite everyone to come and visit and be a part of it and learn how you can go behind the scenes by visiting nasa.gov/social. Without any further ado, though, we're going to jump right into it and learn a little about our mission. With that, here's Aries Keck to introduce our first speakers.
Okay, so we're going to bring Dante Loretta on up here. He is the OSIRIS-REx program scientist, principal investigator, and let's bring Christina Ricci up here. She is the OSIRIS-REx deputy program scientist for HQ. And take it away, Krista.
Hey, everybody. So NASA does some pretty amazing things. OSIRIS-REx is the third mission from NASA's Planetary Science Division's New Frontiers program. The first, New Horizons, zipped past Pluto last July and taught us so many amazing things about that icy body. The second mission, Juno, just entered orbit around Jupiter and is teaching us about that gas giant. But we are really here today to celebrate the launch tomorrow of the third mission in the New Frontiers program, OSIRIS-REx. OSIRIS-REx will be the first NASA-led mission to retrieve a sample and return to Earth that sample from an asteroid. It will also be the largest sample return since the Apollo era. I have been very honored and privileged to work with this team that has been built for OSIRIS-REx, and that includes the man beside me. Dante Loretta is our principal investigator from the University of Arizona, and he's going to tell you about this fantastic mission. So Dante, take it away.
Thank you, Christina. So great day for us on the OSIRIS-REx program. I just drove over from Space Launch Complex 41, where we rolled the Atlas V rocket out of the vertical integration facility and onto the launch pad. And I was privileged to actually walk along with the rocket and see it get ready for launch. So a long time coming. I've been working on this program since 2004, when we originally conceived of the idea of getting to a near-Earth asteroid, collecting material off of its surface, and bringing it back to Earth for analysis in our laboratories. If I could get the first visual up. So what we're doing is we're sending a spacecraft off the Earth tomorrow. We're going to spend about 2 years cruising through space to rendezvous with near-Earth asteroid Bennu. We're going to spend a couple of years mapping it in great detail, first globally, so we can understand what areas of the asteroid are safe, where we think the TAG-SAM device, which you'll hear a little bit more about, can collect the sample, and where is the most scientifically valuable material. And for us, science value is driven by the desire to find organic molecules from the earliest stages of solar system formation that may have led to the origin of life on our planet and maybe other places in our solar system as well. We'll go down for a 5-second contact, grab that material, bring it back on another 2.5-year cruise back home. So 7 years after we launch tomorrow, and plus a couple of weeks, we'll have material back on Earth for analysis in our scientific laboratories. I'm going to use most of our time here to actually answer your questions, so why don't we move into our question and answer session.
Indeed. So remember, if you're following along online at home, remember to ask a question using the hashtag AskNASA, and we've got folks here in the room that are constantly monitoring that, answering either your questions, or we're going to be answering a few of those here to our audience.
So if you're in the audience and you have a question, let's raise your hand. All right, stand up, Fossil Locator. I know his Twitter handle, so we're getting you a mic. Okay.
Hi. So what sort of surface conditions do we know about on this asteroid? Is it going to be, are we collecting dust? Are we collecting small gravel or chunks of rock?
Great question. We've been fortunate on OSIRIS-REx to have conducted an extensive astronomical campaign of our target asteroid. And we've used the best telescopes on the surface of the Earth and in space to understand Bennu. And one of the key questions we ask is, what is the nature of the surface? And we really have 3 different lines of evidence that address that. The first comes from observations using the NASA Spitzer Space Telescope. And this is an infrared telescope, so it's measuring how much heat is coming off the asteroid. And we looked at, as it rotated, how it heated up and cooled down. and we measured a property called thermal inertia, inertia being resistance to change, so resistance to change in heat. Small grains have a very low thermal inertia, and large grains have a very large thermal inertia. And we found Bennu to have a thermal inertia consistent with particles about a ½ inch across or so. So we kind of expect a gravel field on the surface of the asteroid. We also use the radio telescopes at Arecibo and Goldstone to measure how the radar scatters off the surface. And we see that it's really smooth, even at the shorter wavelength of 3.5 centimeters, consistent with the idea that the average surface is on the order of centimeter roughness scale. And then finally, the shape of the asteroid. In fact, this would be a good time to bring Bennu in here. This is the radar shape model that we reconstructed from the Arecibo data. And without even knowing, you could probably tell where the rotation pole is because it's got this ridge around the equator. And in fact, that is the equatorial region, and these are the poles. And this really looks like material is moving down from the poles and collecting there, and that's consistent, again, with kind of a gravelly surface.
Thank you. Dante, during the 5 seconds that it will be extracting, what is the extraction process?
Yeah, we are basically a space vacuum cleaner, is the easiest way to think of it. Now, we can't actually bring a regular vacuum cleaner because there's no atmosphere at the asteroid, so we actually have to bring our atmosphere with us. And so we have 3 bottles of nitrogen gas that are on this robotic arm. If I could hand that back to you, Christina. You can see it really is an arm in the sense that it's got the shoulder, the elbow, and the wrist joint. At the end of the wrist is the filter, or the sampler head. And then on the forearm, that bulge there, those are actually 3 bottles of gas. So we'll kind of create that vortex vacuum action by opening up one of those bottles. And then the gas will entrain the gravel particles, and they'll be lifted up through that air filter and caught in an annular ring. And I think we have some actual engineering hardware of the tag SAM you'll be able to see a little bit.
So is most of the communication for the OSIRIS-REx already pre-programmed into it, or once it gets to the asteroid, are you all going to be communicating with it directly from NASA? And if so, like how long is the lag in between communication?
The OSIRIS-REx team will talk to the spacecraft almost every day. And you can see when you look at the spacecraft, you see that white dome that's pointing off to the right. That's a 2-meter antenna, radio dish, basically. And so that's where we get most of our information. We have a couple other antennas which much lower data rates, 40 bits per second, I think, on the low gain antenna. So you're just getting a little dribble of information. But with the high gain, we get all of our information. So we will be constantly planning and replanning what we want the spacecraft to do while we're in cruise phase and while we're in operations around Bennu. And the time that it takes for a signal to travel from the Earth, we'll be using the Deep Space Network antennas. They're in Madrid, Canberra, and Goldstone, California. It can vary up to as many as 18 minutes one-way light time and as low as about 10 minutes, depending on the phasing between the Earth and the asteroid.
How fast is the asteroid actually going?
The asteroid is in orbit around the Sun, and so it's going about the same as the Earth is. So in fact, that's one of the reasons that we can access it. We need to change our velocity relative to the Earth by about 5 kilometers per second. That's going to be somewhere around 8,000 miles per hour or so.
One of the things I want to add to that real quick is the rotation period of the asteroid, because that's what we're really going to be trying to match up with as we're doing our observations near the asteroid. So it rotates at a period of about 4.3 hours.
Why did you select Bennu to go and excavate?
Why don't you take this one, Christina?
Sure. So the science team carefully selected Bennu after 3 critical criteria. They looked at the accessibility of the asteroid. We needed something close, a near-Earth asteroid, and its orbit is about 1.2 years around the Sun, and it passes by Earth every 6 years, so it was easy for us to get to and from. Second criteria was the size, so that we can enable those close proximity operations and the actual sampling of the asteroid. It has an equatorial bulge of right around 492 meters, and it has that orbital period of 4.3 hours. So it's spinning at a rate that we can actually do the proximity ops and the sampling. And then the third criteria was really the composition of the asteroid. So this is a carbon-rich asteroid, and we know the geologic context of it. So we're hoping to retrieve those organic molecules that Dante mentioned earlier and understand more about not only the evolution of our solar system, but potentially understand the precursors to life, either here on Earth or elsewhere within the solar system. So it was really those 3 criteria.
Can you tell us about what sort of long-term threat Bennu poses to Earth and how OSIRIS-REx will study that?
Right, I'll get it. Sure. So Bennu, by virtue of the mission design and the accessibility that Christina discussed, it is what we would consider a potentially hazardous asteroid, which means it's greater than 150 meters in diameter, and it makes regular close approaches to the Earth. And one of our science investigations is to evaluate its long-term orbit or trajectory into the future so that we can understand what is the likelihood that it may impact our planet at some point in the future. So what we're focusing on OSIRIS-REx is a non-gravitational force that we call the Yarkovsky effect that substantially changes the position and the orbit of this asteroid because it integrates over long periods of time. Since we've been tracking Bennu, starting in 1999, we've seen it move along track about 160 kilometers as a result of the Yarkovsky effect. That, by incorporating that into the orbital solution, we're able to calculate the likelihood that it's going to impact the Earth. It's about less than 1/10 of 1% chance. So better, you know, the optimist would say a 99.9% chance of not hitting the Earth. And that, if those events were to occur, they would be at least 150 years in the future.
Sure. We have a question from social media. This one is asking, if the OSIRIS-REx mission provides successful results, will another mission like it be done in the future?
So we intend to use the technology that's been developed for this mission, for future missions, of course. We've managed to develop technology to enable us to be in orbit around a low-gravity body like Bennu. You know, a lot of the thrusters and technology that's here is going to be used for future missions. So we're not fully saying that there's going to be another small body mission soon, but of course NASA explores, it's what we do. And this is just another successful example of NASA doing the next big thing. So
I have a three-pronged question. It's from two fourth graders at New Prospect Elementary School in Alpharetta, Georgia. Sahi and Cade want to know, how will the sample come back? Does the small collector have a rocket? And when it comes back to Earth, how will you find it?
All very good questions. So we will be bringing the sample back inside that air filter or that TAG-SAM head. That's basically the collection chamber where all of the material that we gather will be stored inside of. That will get passed over to a sample return capsule, which is roughly the size of a large pizza and opens up like a clamshell. We put the head in there, and then we have some separation bolts that allow us to separate the head from the arm, and then the clamshell closes and the sample head is protected in there with its precious science treasure. When we come back to the Earth, we'll bring the whole OSIRIS-REx spacecraft back to the Earth, and then about 4 hours before we would hit the top of the atmosphere, we'll release some more separation bolts, and there's actually a compressed spring that will release and twist and send the return capsule into the atmosphere. We want it to twist because that gives you stability. Just like when you throw a football, you do a much better job getting that football where you want it to go if you give it a nice spin, a spiral to it. We want to get that spiral on our sample return capsule, and that's coming into the Utah desert, just to the southwest of Salt Lake City. It's going to hit the top of the atmosphere at about 27,000 miles per hour, and it's going to create a great fireball, plasma, as all that energy dissipates through friction with the Earth's atmosphere. That'll remove most of the energy. And then when we hit free fall velocity, about 3 miles above the surface of the Earth, our parachutes will open up, and we'll come down gently for a landing in Utah.
I've got a question here. You described your belief as to what the surface of Bennu looks like via telescopes and things like that. Have we done any correlations between pre and post Rosetta as far as what our best guesses were for that asteroid versus what our reality was with that asteroid?
We did not do it for Rosetta and Comet 67P because we didn't have the same kind of data. It's hard to get observations on the surface of the comet because when it's within observing conditions, it's got the coma around it, so you don't get the same kind of information. But we did do it for asteroid Itokawa, which was the target of the Japanese Hayabusa mission. And so that was a really great ground truth for us. We did the same kind of measurements with the Spitzer Space Telescope. We got a much higher thermal inertia value for Itokawa, which would suggest, based on our theory, that it has a larger grain size than the centimeters or so we expect for Bennu. And indeed, when we look at those awesome images that our colleagues from the Japanese Space Agency brought back from that asteroid, we see a lot of rugged terrain, a lot of large boulders, and only a few small patches of the gravel fields that we want to study. So in fact, we took the strategy on the team, and I said early on, we think Bennu is a kind of a nicer place to go just to operate and get a sample, but I want you to design your mission to sample Itokawa, because we thought that would be a driving case, kind of a tougher case, and if we could literally crack that nut, then we would probably have a better time at Bennu.
Thanks.
You're not landing on Bennu, you're kind of hovering above it. My question is it, since it's rotating it, is it in a naturally geosynchronous orbit, or because of the low gravity, does it need rockets to either keep it from flying away or to keep it from crashing into Bennu?
So most of the time when the spacecraft is in orbit around the asteroid, we have to be in what we call the solar terminator plane, basically 6 a.m. and 6 p.m., because the gravity field is so low that the solar radiation pressure is constantly buffeting the spacecraft around. And if we were to try to orbit in front of the surface, like over noon, the pressure would push us right in and we would crash into the surface. We don't want to do that. And so we have a whole series of maneuvers that take us from leaving orbit. We call that the orbit departure maneuver. We hit a checkpoint, which is about 125 meters over the spot where we want to get to. Then we drop down to the surface and we do a final maneuver we call the match point, and that gets us in essentially into a geosynchronous kind of attitude where we're hovering over the spot where we want to get the sample, and then we just use a little bit of thrust and Bennu's gravity field to pull us in for that gentle high five sample acquisition event.
So are you actually orbiting Bennu, or are you in a heliocentric orbit along with Bennu? How do you orbit such a low mass object?
OSIRIS-REx has the really awesome capability of doing everything. We are going to do hyperbolic flybys so that we can measure the mass as we look at the deflection of the asteroid. We're going to be able to station keep over certain areas on the asteroid as we do our survey global mapping stations, and we will go into orbit around the asteroid. And so because the gravity field is so low, because the mass of the asteroid is small, it doesn't require a lot of thrusting with our rocket engines to make those kinds of changes. You would never be able to do this with a Mars orbiter or an Earth orbiter, for example, because the gravity field is so high. Even small changes in the orbit around those bodies require a substantial amount of resources. But we can hover like a hummingbird. You know, we can orbit around the thing. We can go in for that sample acquisition collection maneuver, and we will only use a very tiny amount of our rocket fuel.
This is another question from social media, and they ask, do you expect to find any magnetic fields around the asteroid?
The OSIRIS-REx spacecraft does not have any equipment that is designed to measure the magnetic fields around the asteroid, so that wasn't part of our science investigation. And in general, we expect magnetic fields to be developed in much larger planetary bodies that have separated into a metallic core and a rocky mantle. And because Bennu is, we believe, a primitive asteroid, it never went through that extensive geologic processing that would generate what we call a differentiated body like that. And it's one of the reasons we're really interested in it, because it's kind of got all of the building blocks of that asteroid intimately mixed together. So when we do the sample analysis, we'll be able to piece it together, you know, bit by bit.
Okay. And one more question from social. Why is the asteroid named Bennu?
Okay. So the OSIRIS-REx mission, along with the Planetary Society and the Linear Asteroid Survey, worked together with NASA to run an international naming contest. When the asteroid was originally discovered, it was given the awesome name of 1999 RQ-36, which is really a catalog number that tells us when it was discovered. And so in order to get it named, we went through this great contest. Michael Puzio, who was an elementary school student, submitted the name Bennu. It rose to the top of the committee selection because it ties to the Osiris mythology. Bennu is an Egyptian heron, born of Osiris, represents creation and origins. And he said that the spacecraft looked like a heron in flight when it was going in for the sampling, and it had its solar rays extended in that Y wing configuration and the sampler arm down to grab the sample. So we thought that was really cool.
We have time for one more question from the room. Go ahead, stand up, sir.
So I do work on patient samples, and sometimes we use a sample only to wish that we had asked a different question or use a better technology a few years later. So I'm wondering, how do you balance the desire to get everything out of the sample versus knowing that there might be a better technology or a better question 5 years later? Do you save some of it?
So we're going to be bringing back somewhere between 60 grams and 2.2 kilograms of sample. 25% of that is going to be reserved for the science team in order to meet all of their mission objectives. Another 75% is going to be stored at Johnson Space Center's astrocuration facility in order for future generations of scientists to really ask those questions we haven't even thought of yet, or use the technologies that haven't even been invented yet. So this is going to be the gift that keeps on giving, much like the Apollo samples.
All right, thank you. Let's hear it for Dante Loretta, Christina Ricci.
Oh, yeah.
We got the secret tag high five. Right? Give it back to me.
Oh, we got to measure the sample.
There you go.
There you go.
All right, thank you. So now we're going to hear a lot more about the spacecraft itself and all the engineering that went into it. So let's bring Tim Lin up here from Lockheed Martin. Mike, come on up.
All right, thank you.
Take it away, Tim.
All right, thanks. I'm Tim Lin. I'm the Chief Systems Engineer at Lockheed Martin. Really worked with an amazing team at Lockheed Martin and really across the U.S. We had a number of partners, universities and contractors across the country. So it's been a huge endeavor. At one point, I think we had 900 to 1,000 folks, with their hands in the design of OSIRIS-REx. And so what I'd like to do is talk a little bit. I have a bunch of pictures and a few videos. I'd like to put some context into the great description that Christina and Dante just gave about our mission and about the spacecraft. So the first picture, please. It's the nice thing about OSIRIS and what we try to do at Lockheed and in general is, these are really, we try to keep the missions really simple, really robust. And one thing we've been able to do is really leverage a lot of our other missions that are currently flying around other bodies. We have a couple of Mars missions, MRO, MAVEN. We have Juno, which is currently orbiting Jupiter. And so we've basically taken a lot of those technologies and we've installed them in the basic capabilities of the OSIRIS-REx spacecraft. This is in Atlo when it's first getting built up. You can see the core structure. You can see the harnessing, tens of feet of harness that go into laying out the electrical work on OSIRIS-REx. So this is kind of early in the stage. If we go to the next picture of the spacecraft, this is where it's basically integrated. We're now starting to do the test program on OSIRIS-REx. One thing we do once we get the spacecraft completely built, we have to make sure they can withstand the environment of launch. Launch is really the dramatic environment that it has to withstand. And so we're getting ready to do some testing at Lockheed Martin in Littleton, Colorado. It's got the solar arrays on, it's got the TAGSAM on, it's got all the payloads on, and it's ready to go through an extensive test program. Next chart. This is the spacecraft now kind of going towards the end of the test program. One thing we like to do, we need to do as well, is make sure that the spacecraft can withstand the vacuum of space, the extreme temperatures that it's going to go through. So at this configuration, the spacecraft's now fully encapsulated in MOI and the blanketing, and it's actually being lowered into a very large thermal vacuum chamber. It's going to be put into this chamber, and it's going to basically see the same environment that it's going to see in space in terms of vacuum, as well as we have a solar simulator that simulates different sun ranges like it's going to see during the OSIRIS-REx mission. Next one. This is kind of the top view of the spacecraft. It gives a great example of all the really key scientific instruments that are on board. OSIRIS-REx is blessed with all of the capabilities between the camera systems from the University of Arizona. We have 2 spectrometers from Goddard as well as Arizona State University. We have a Canadian Space Agency provided OLA instrument, which does our lasing and does the topographic mapping of OSIRIS. And we have an instrument from Harvard MIT, basically a student provided instrument called Rexus. And so that along with some engineering cameras, and of course there on top is the SRC, that's a sample return capsule, that's the clamshell that Dante mentioned, where the TAGSAM head will get installed, and that's the one that actually comes back to Earth. So that's really where all the action is, and then the next chart is really the TAGSAM, and I'm going to get into a little more detail about the TAGSAM, but the TAGSAM really is, I like to think, the heart of the mission. That's the one that, obviously, the instruments are going to give us top to bottom what the asteroid is, the makeup of the asteroid, but the TAGSAM is the one that's going to go and actually do the sampling and bring back a sample. This is a sample return mission. Bringing back a pristine sample is what this mission's all about. And so here at the spacecraft level, you can see the TAGSAM arm. It's about 10 feet in length. It is basically a pogo stick. It's got this constant force spring that allows us, when we make contact with the surface of Bennu, it actually compresses, it provides a positive force so that the head stays in contact with the surface for that 3 to 5 seconds. We fire the gas bottles, that mobilizes and fluidizes the regolith and then gets collected in the head, and I'll talk a little bit more about that here in a little bit. But here we're doing system level testing at the spacecraft to make sure that before environments, after environments, and before we button up for launch, this arm does everything we need to. So if we go to the first video, I want to go into a little more detail about some of the testing we did before we actually installed it on the spacecraft. So again, this is in Littleton. Here we are. Here is the arm in its stowed configuration. Here it is in the launch container. This basically keeps it stable during the launch environment, and there's the TAGSEM head inside there. This is a view of that TAGSEM head. It's a design, really, that we needed to ensure a couple of things. One, that here it's on an air-bearing table. When we actually do the touch and go, this is an example with a simulated spacecraft, that it has a U-joint that allows it to form to the actual surface when it makes contact with Bennu. As well, and then here's some actual sample collection that we're actually doing. So we did huge amounts of collection to make sure that we really were going to collect at least 60 grams and more like 2 kilograms, as Christine said. And this is an example of some testing that we did and shows the amount of material that we were able to collect. It's a very simple design was the idea. It was actually developed about over 10 years ago. The lead engineer basically used a plastic cup. And this is the actual TAGSEM head itself. But he started with a plastic cup and an air compressor in his driveway, and really wanted to say, okay, how well could we really mobilize this regolith? How well can we really, generate, fluidize the regolith so that it can be collected? And so we started that, and over the course of that 10 years, he really came up with a very simple but novel design. And really, it looks a lot like an air filter, and Gary's actually sending around a 3D printed model of it. But the idea is this is kind of like, again, like a 1970 Ford air filter. It's perforated, so it allows all the gas to escape, but the regolith gets trapped on the inside. There's the U-joint on top, which again allows it to form. Fairly simple device. On the bottom, there's a series of contacts, Velcro pads, which allow us to collect surface material. So we collect both surface material as well as bulk material when we actually do the tag event. So fairly simple device, but very novel and does a great job of collecting a loose material, which is what we expect when we get to the asteroid. So let's go to the last one. And so now I wanted to go into a little bit of detail. Thanks, Gary. A little bit of detail about then how does it actually get used during the mission. So that was the spacecraft, that was the TAGSEM arm and the head. And here's a simulation of it actually getting deployed. The arm gets deployed, and it is a single plane arm, like Dante said, wrist, elbow, shoulder. And here we are going into to actually do the touch and go collection. This is a great example of basically how it works. So the gaseous nitrogen gets sent down, fluidizes, mobilizes the material. The gas escapes, but the regolith gets trapped inside the TAGSEM head. Here's the spin maneuver that Christine and Dante were doing as they were heading off the stage. And that actually verifies that we got enough sample. It checks the change in mass properties, and that confirms whether we've collected at least 60 grams or not. Once we confirm it, we open the clamshell, insert it into the SRC, close the SRC, bring the whole spacecraft with the SRC back to Earth, and the SRC then re-enters the Earth's atmosphere. Like Dante said, around 27,000 miles per hour, slows down to 10 miles per hour before it touches. Primarily from that PICA, that heat shield, that really absorbs all the heat. Upon peak heating, that heat shield gets to about almost 5,000 degrees Fahrenheit. So it gets very, very hot. It actually ablates off to keep the thing cool. On the inside, though, the avionics stays cool. So it's a great heat shield to ensure success. And then we have a series of parachutes. One that takes us from supersonic down to subsonic. That's our drogue chute. That deploys, and then we get our main chute, which drops it lightly down onto the surface at about 10 miles per hour. So a very slow drop onto the Utah test range. So that's kind of it in a nutshell. That was all pretty quick, but again, the really key thing that we try to do when we built the spacecraft is really, again, try to draw from that heritage, make sure that we could leverage that heritage as much as possible. But then the innovation really here is that TAGSEM arm, and integrated that into the design to support this unique mission to the asteroid.
All right, with that, we're going to open up for questions. Again, if you're following us online, you're welcome to ask a question using the hashtag AskNASA.
So you said it knows how much mass it collects. So if it doesn't correct the proper amount of mass, will it be able to return back to the asteroid to get more?
Yep, that's exactly right. So we have a really novel approach to we basically know the mass property. We spin it before we ever go down to the asteroid, and we confirm what the mass properties are, really the inertia of the spacecraft. We then go do our collection, back away, do the same exact test, and see if it's changed by the amount that it should have to ensure that we caught at least 60 grams of regolith. If for whatever reason we didn't, we have a total of 3 bottles, so it gives us 3 tag attempts. We can actually go back down, say we got 30 grams, we can go back down and do a whole nother collection. That'll just add on to what we already had in the sample collection. So it gives us a really robust approach. Obviously, we really believe, based on all the extensive testing we did, that we're going to be successful on the first attempt, but we do have 3 attempts, and each one adds more regolith to the overall accumulation. So, yep.
Hi. I was discussing the mission with my son, and he was especially concerned about the retrieval of the asteroid material. He looked at me and he said, have they not seen Andromeda Strain? But seriously, is there a quarantine protocol of the material when it comes back?
So I guess twofold. One, we do know this asteroid is basically, no living bodies on this asteroid. It's been pelted with radiation for well, billions of years, right? It's the remnants of the early solar system, so 4.5 billion years ago. So we know by that process alone that there's nothing living on the asteroid. But part of the process that we're doing is we're making sure it's a pristine sample. So we are managing the sample and the SRC in the utmost care, really to ensure the sample is pristine and taken care of. But in that process, we really also manage it in terms of, getting out and being contaminated or contaminating anything outside of it. So we truly believe there's nothing living or any kind of concern for Andromeda strain. But at the same time, we take all the precautions really to keep it pristine all the way out to where it's being curated at Johnson Space Center.
Hi. I just wanted to ask maybe a couple of questions to kind of follow up with that last question. Are there any instruments on board that will actually be doing any kind of science on the sample on the way back? And secondly, where exactly is this asteroid in orbit? Is it part of the Oort cloud, and is there any concern, is there a point in this mission that you might be going through other bodies out there that could cause problems?
Yeah, so the first part, there is nothing on board that we do any in situ measurements. I mean, we do have spectrometers on the spacecraft, so before we ever go down and take a sample, we'll have mapped the asteroid from top to bottom. So we already know quite a bit about this asteroid from ground-based, from Arecibo data that Dante mentioned, as well as Spitzer and space assets. When we get there, we're going to obviously even know more. The spectrometers are going to tell us something about the mineralogy, tell us about the thermal properties, some of the geology of it as well. But once we get the sample, we're not going to analyze the sample. It's going to stay pristine in the SRC clamshell until it gets back to Earth. In terms of other bodies, we do know that there are a lot of natural satellites, and one of the things that this is an asteroid that is a NEO, so it's a near-Earth object. It stays pretty close to the Earth's orbit, and it does come in close proximity of Earth every 6 years. And we also know there's other natural satellites around this asteroid. So one of the things when we approach Bennu, one of the things we're going to be looking for before we get really too close is we're going to start looking for, are there any other natural satellites around this asteroid, just to make sure that we're going to be able to successfully get to Bennu, start to do all of our operations around Bennu. Yeah, this mission's amazing for a number of reasons. One, just to learn how to deal with these kind of bodies, these kind of small bodies, how to operate around these kind of small bodies, to understand if there are natural satellites, other small satellites around these kind of bodies, and make sure that the spacecraft stays safe in that process. So this really is the first, and I think Christine said that, this really is the first of a long line now of missions that will give us the capability to go to asteroids, human missions to asteroids in the future. So we're taking all the precautions to make sure that we are safe, but something that we have certainly thought of, and something that we're going to be watching for as we approach Bennu.
All right, thanks so much. Let's hear it for Tim Lin. Thanks, you guys. So we're following all the TagSam selfies that are going around the room. That's great. Also remember, if you're watching us online, use hashtag AskNASA, and also make sure to tag the OSIRIS-REx account on there, which is at OSIRIS-REx on Twitter. Really straightforward. Let's bring up our next 2 speakers. It's Jermaine Oliver. He is the OSIRIS-REx flight design analyst. Come on up, Jermaine. And Gordon McElmore with ULA. And they're going to talk a lot about how they're actually going to get to Bennu and back. So, you guys ready? Take it away.
I'm ready. Good afternoon. I'm Jermaine Oliver, flight design analyst for the OSIRIS-REx mission for Launch Services Program. LSP basically matches satellite providers with launch vehicles based on size, cost, destination, and weight. LSP has various different roles in this matter, to bridge the satellite with the launch vehicle provider. And my job as the trajectory analyst is to ensure that the launch vehicle reaches the spacecraft's requirements and meets them, and also ensures that the spacecraft reaches its final destination. Given all that, I have a video I want to show that can kind of explain a little bit better. Turn it on, please. Pause it right there, please. Okay. Where you're looking at now is where we drop the spacecraft off at. I say we, the launch vehicle, drop the spacecraft off at here at this point called the target interface point. That's basically the agreement made between the spacecraft and the launch vehicle of where we're going to drop the spacecraft off at and where our target should be realized. As you can see, we're a little bit past that now, and this is OSIRIS-REx. You can see the Earth. Bennu is here in its orbit, and the rest of the solar system. You can continue, please. As we go through, you see OSIRIS-REx is trying to play catch-up to Bennu, but it has to go through several different maneuvers to get its orbit just right, to ensure that you get to the exact point at Bennu at a particular time. And those are called deep space maneuvers. We do 2 of them before we do our Earth flyby, and you'll see the Earth flyby momentarily. But ultimately, the Earth flyby is basically Earth providing gravity assist to OSIRIS-REx to give it an extra bit of velocity to line up with Bennu. As you can see, the orbits are now beginning to line up a little bit, and that flyby is giving OSIRIS-REx the extra speed it needs to reach Bennu. Now, as we get closer to Bennu, you'll notice that we'll do some last-minute fine-tuning of the trajectory to ensure that we get right there at the Bennu point. As you can see, we're getting very close now to get right at the Bennu point and rendezvous with Bennu. So it's kind of like a rendezvous mission from my perspective. And we'll see in a couple of seconds the last few maneuvers as we zoom in on this. This is using our free flyer software made by AI Solutions. And you see right here the last few burns right here that will get us right there in front of Bennu, and you'll see it right there. As you see, Bennu's right there, and OSIRIS-REx is prepared to begin its study and begin its spacecraft science. That's all I have for the moment right now. I'll pass it on to Mr. Gordon.
Afternoon, guys. So I'm here from United Launch Alliance, and we're always excited when the guys like Jermaine and the LSP guys over at NASA give us a call and allow us to have the opportunity to work on a mission this critical and this important. So United Launch Alliance, a little bit about us. I actually work at the main production facility in Decatur, Alabama, if the accent didn't give it away. So the launch vehicle that you guys see tomorrow is an Atlas V. The configuration is a 411. We'll talk a little bit more about that in a second. So we currently manufacture the Delta IV and the Atlas V launch vehicles. Most of that production does happen in Decatur, Alabama, like I said. We have some parts for the Atlas V that come in from Harlingen, Texas, such as the payload fairing that you're going to see on tomorrow's mission. The 411 is one of the configurations of the Atlas V, and what that means is it is a 4-meter payload fairing. So that's the first digit in the 3-number configuration. Then the second number, the 1 for this particular one, is 1 solid rocket booster, or SRB as you'll hear us. We love our acronyms. And then the last one is a single engine Centaur. So the Centaur is the second stage. If you guys will take a look at this slide here, you can see the first stage, which is started there by the RD-180 engine. Then you've got the solid rocket booster, as well as the entire structure, the propellant tank, as well as the liquid oxygen tank. Then you have a Centaur interstage adapter, followed by the Centaur and the payload fairing, which encompasses the OSIRIS-REx payload. We actually have a video that we'll share with you guys that actually will show, if you do watch the launch tomorrow, exactly what we'll be going through and happening on the launch. So if you guys can play the mission profile video.
The following profile details the important events of this mission using approximate times.
6, 5, 4, 3, 2, Atlas engine ignition, 1, 0, and liftoff of the Atlas V rocket carrying the...
The Atlas V RD-180 main engine and a single solid rocket booster ignite to lift the vehicle away from the pad. Shortly after liftoff, Atlas begins its initial
up on the
pitch, yaw, and
countdown,
roll
the
maneuvers to
RD-180
attain
and
the
the
proper
SRB will
ascent
come to
profile
life
and minimize
and
aerodynamic
start its
load.
approach into space within a
Atlas V
minute. So I
reaches
think about
Mach 1
exactly
with a speed of
54
sound at
seconds, we'll hit Mach 1. And within 2.5 minutes, the SRB will jettison. You'll see that very shortly.
The solid rocket booster
And
is
at
jettisoned
that
in
point,
less
we'll
than
be
2.5
traveling about 12,000 miles an hour.
As it approaches
So
booster engine
we're
cutoff,
burning
the Atlas
propellant
V
at the
is
rate of
burning
about
propellant at the rate of
1,600 pounds per second.
1,672
If anybody wants to chip in on a little extra gas money, we would appreciate that. But within 4 minutes, the first stage booster will be completely used up. And that equates to 25,000 gallons of RP1 rocket propellant, as well as 50,000 gallons of liquid oxygen. So you're about to see the separation that will occur right at about 4 minutes. And then about 10 seconds later, the payload fairing will jettison, will actually break apart. You'll see a good display of that. And then we have several RL-10, which that's the engine for the Centaur startups, and then goes through some coast phases as well. But you can see there about 4 minutes and 10 seconds into the launch, because of how fast we're burning propellant, this spacecraft only weighs about 6% of what it is on the launch site, so, or on the launch pad. Our ULA's portion is only about an hour of this mission. So, you know, within 58 minutes, almost exactly, we will turn the payload back over to NASA. So we'll open it up for some questions if you guys aren't questioning out.
Let's get some mics down here. There we go. Awesome.
You talked about chipping in for gas, so I was just kind of curious, what's the overall cost of this mission, and how much of that is attributed to the science portion, how much is attributed to the launch vehicle and whatnot?
So I'll let Jermaine answer that one if he wants to. From the NASA side, it is a NASA mission.
Yeah, the spacecraft total cost, I'm estimating about a few $100 million. I don't have the exact numbers in front of me, but it's pretty expensive. As far as the breakdown between spacecraft and launch vehicle, I don't have that breakdown in front of me right now. I'm sorry.
This question is from social media, and it's from Nico, an 11-year-old homeschool student, and he asks, what happens if OSIRIS-REx accidentally slingshots instead of orbiting?
I'll definitely let Jermaine answer that one. We will claim no, ULA won't have anything to do with that.
Okay. When OSIRIS-REx does that slingshot maneuver around the Earth, the last few maneuvers slows it down so it can land right at Bennu at the exact point. So those last 4 maneuvers you noticed, they was basically slowing down OSIRIS-REx to get to that point.
Great question, though, Nico.
Do you happen to have any parts of the rocket that are going to be reusable? I mean, none at all?
Not at all. Currently, this is a EELV, Evolved Expendable Launch Vehicle, so none of what we do is reusable.
I don't build rockets, but looking at the ones in the shop, you have main engine and then just kind of one sticking on the side. It would seem like that would make it tip over. Can you explain how that works?
Yeah, and we get that question a lot, especially on this. So this is the 4th time that ULA has launched the 411 configuration of the Atlas V. And basically the booster engine, so that first stage of the rocket, we can do what we can gimbal with it. So it actually is, you know, not a steering wheel, obviously, but we can adjust the balance, per se. Is that kind of what you were asking? So it gives us the ability to, basically steer it.
Other questions? Just a reminder for folks who are online that you can ask questions during any of our Q's and A's today using the hashtag AskNASA. So with that, thank you, gentlemen, for joining us.
Thank you for your time.
Thanks, guys.
Thanks so much. Remember that if you're online, you can go to hashtag AskNASA, and we'll have somebody here in the room is answering them, and we're also going to ask them to our people. We're going to bring down Danny Glavin now. He is an astrobiologist at my home, NASA Goddard, and he's going to talk about what's going to happen with the sample when we get it back here on Earth. So, Danny.
Okay, thank you. Okay, good afternoon. I'm really excited to be here. I kind of have to pinch myself. I can't believe, we're getting ready to launch this thing. It's been many years of work getting ready for this mission. As was said, I'm an astrobiologist at NASA Goddard Space Flight Center. A little over a decade ago, Jason Dworkin, who's a project scientist on this mission, and myself established Goddard's Astrobiology Analytical Lab. And what we're most known for is the analysis of organic compounds, the building blocks of life in meteorites. And I know we're both really excited when these samples come back 7 years from now, land in Utah. We're going to be very eager to analyze these things, to search for some of these building blocks. We've been looking at meteorites for, like I said, over a decade now. A specific type of meteorite called a carbonaceous chondrite, which we think are similar to the samples that will be returned from Bennu. And it's just amazing the chemical diversity in these meteorites. I mean, you find amino acids, the building blocks of proteins and enzymes that basically catalyze all the reactions in biology on Earth. There are 20 in life, yet in some of these meteorites we see hundreds of amino acids, some that don't even occur naturally on the Earth, so they truly are extraterrestrial in origin. That's just fascinating. In addition to amino acids, we see nucleic acid bases. These are the ACGT you learn about in biology, the genetic code in DNA and RNA. And these compounds are in the meteorites themselves. So you can think of these asteroids as literally prebiotic chemical factories that were producing these building blocks of life 4.5 billion years ago, before Earth formed, before life started here. I don't know about you, that kind of gives me goosebumps, to think that our building blocks were being formed in these asteroids. Now, although meteorites have provided a wealth of knowledge about organic compounds, they don't tell us everything. There are a couple problems with the meteorites that come from asteroids. Most we can't really pin to a parent body, so we don't really know where they come from. We find them, great, they probably landed a few thousand years, but we don't know what asteroid they came from. And secondly, which complicates some of our analyses, which I'll talk about here in a second, is that as soon as these meteorites enter the atmosphere, they're immediately contaminated by the atmospheric gases. As soon as they hit the soil, they're contaminated by organics and even bacteria in the soil that can complicate your analysis. So the samples from Bennu will really be the first time that we get a pristine sample from a known body to study. So really excited about that. I think we're going to learn a lot about prebiotic chemistry and, frankly, probably discover things that we never expected. I'm sure Bennu's got some secrets for us to uncover, for sure. If you could pull up the first slide. Just want to talk to you briefly about some of the analyses we do at Goddard, looking for these organic compounds, these building blocks of life. It's not a trivial process, actually. You can't just pick up a rock and throw it in an instrument and out spits the data. It actually takes some time. So we get chips here in the top left, something about the size of a sugar cube, so a very small amount of the sample that will be returned. We actually crush it up into a powder, something like the consistency of flour. And the reason for this is we want a lot of surface area material so that we can extract the organic compounds from the powder. So we call this making a meteorite tea. So we actually heat the samples in liquid water in sealed tubes at 100 degrees Celsius for 24 hours and extract all the good stuff. So this is where all the amino acids, the nucleic acid bases, if they're there, and other important building blocks of life will be extracted. So it's kind of a dirty water. Definitely wouldn't recommend drinking this stuff. So we actually have to purify it. We have to purify it to remove the salts and some of the metals. And then the last step, which is about a week to do this, we inject it into our chromatography instrument. So we can use gas or liquid chromatography to separate the organic compounds and then measure their mass, which is what we use to identify them. And this is really an important step here. In fact, analyses have shown that there are millions of different chemical structures in some of these meteorites. And so you really need to be able to separate them using chromatography to identify them. That's kind of our process. So I'm open to questions.
So you burn off or extract the inorganic from the organic compounds, but aren't there things we can learn from the inorganic compounds as well?
Absolutely. So I'm biased. You know, I'm an astrobiologist, so I'm focused on the organic chemistry. But these samples are going to be investigated with the state-of-the-art instrumentation for mineralogy, you know, elemental abundances, isotopic measurements, you know, lead-lead isotope dating. We'll be able to actually date some of the minerals that formed in this rock, which is pretty exciting. We'll learn about the timeline and the origin of the solar system from samples from Bennu. So yeah, a lot more than just amino acids. I didn't mean to simplify it like that, but this is my expertise.
Yeah, I was wondering, kind of along the lines of that. So you're an astrobiologist, so you might not want to answer the question, but what types of minerals and elements could you find in there that may have future uses for like mining if Earth's resources were depleted or such like that?
Yeah, so yeah, I mean, in situ resource utilization is kind of a big thing now. You hear a lot of people talking about actually, you know, capturing an asteroid and mining it for, you know, rare metals potentially, or other resources, water, frankly. These asteroids are loaded with water. There's been discussions about using some of that resource as fuel, right, for astronauts traveling outbound. So yeah, certainly in situ resource utilization is something that people are actively looking at, and how we can use these small bodies to achieve some of those goals for exploration. Yeah.
I have a question in two parts. I'm interested in the origin of the prebiotic molecules in
Where's
the
that question?
asteroids.
Oh, yeah, hello.
And are the prebiotics on the surface of the asteroid or throughout the entire mineral, and what are the thoughts behind their origin?
Yeah, so we think that, well, they're scattered throughout, is a short answer, not necessarily just attached to the surface. We see these organic globules in some samples. One of the theories is that, you know, early on you have these asteroids that are basically icy bodies, and they contain precursors from the interstellar ices that were incorporated into the object. So you have ice and very simple hydrocarbons, aldehydes, ketones, HCN. And then as the asteroid, through radioactive decay of short-lived isotopes, there's a heat source inside these bodies that can melt that ice and drive chemistry. So reactions such as a Strecker cyanohydrin synthesis could produce a lot of the amino acids, frankly, that we see in meteorites. And so we think it's parent body chemistry happening during this alteration period where you have radioactive decay and heating inside the asteroid that's producing these complex organics.
So watching the video of how they're collecting the samples, it doesn't look like they're getting very deep within this asteroid. And after 4.5 billion years of just being bombarded with solar radiation, as an astrobiologist, do you think that will affect maybe the molecules that you're able to discover that may be broken down by photolytic sunlight?
Yeah, I mean, certainly, you know, solar, galactic, cosmic radiation. The UV radiation I'm not as worried about because that's usually just the top surface, and TAGSAM will be getting, you know, regolith, you know, several centimeters deep. So it's really this sort of question about what effect ionizing radiation will have. We've been doing some experiments in the laboratory to look at that. So far, our results seem pretty encouraging that, you know, even after millions of years of galactic cosmic ray exposure, you don't do severe damage to the amino acids, but it's definitely something that we're going to be looking at. And frankly, I think that's why this collection's so interesting, because with meteorites, you have no idea where they come. They come from the surface, subsurface, but with this sample, we know they come from the surface. So we'll be able to look at these kind of effects, which is a first.
Hi, you mentioned that, so there's like 20 amino acids and that we've been able to like discover or find more than that. Is there any like understanding as to like the value or the purpose of what these other amino acids do?
Yeah, so this is a good question, right? So we're kind of building up this inventory from our meteorite analyses of organic compounds that may have been available for the origin of life in this prebiotic soup, if you will. And I'm certain we're going to learn a lot more from Bennu as well. And we basically kind of feed that data into these, you know, sort of real prebiotic chemical, people who were working on the origin of the first RNA molecule or the first protein, and telling them, hey, these are the compounds that we likely had to work with on the early Earth. Frankly, it's still kind of a mystery why those 20 were selected. Only about 10 of them are actually abundant in meteorites, so there's 10 that were formed later. But why those 20? It's kind of an open question. Clearly, for just looking at it from a chemical evolution perspective, there were a lot of compounds to choose from on the early Earth from the delivery of these types of objects.
All right, so speaking of open questions, I know we have more questions online and some more in the room, but we're going to have a wrap for that. Thanks so much, Danny Glavin.
Yeah, thank you.
Appreciate it. Thank you guys all so much for joining us. Make sure you tune in to watch the launch of OSIRIS-REx. It's Thursday, tomorrow. The launch time is 7:05. Thanks so much for joining us here at NASA Social. Keep the questions coming on #AskNASA, and we'll keep answering them. And thanks again. Go Rex!